today شباب the last chapter, which is the engine performance. We have talked actually in the preceding chapter, we talk about the engine type, engine classification. Sorry شباب. We talk about engine types, engine classification. We talk also about some different topics related to the fuel and some details of the combustion chemistry, the thermodynamics of combustion, the application of the first law. Even we have detected actually what is going on inside the piston through what's called the engine cycle, and we have considered starting from the air standard cycle, we have to move little bit to the little bit complicated cycle, air to fuel cycle, and then we have moved to the actual cycle, and we have seen the difference, and we have seen actually how to calculate the thermal efficiency of any internal combustion engine, and also how to calculate the power output. This power output that we have learned how to calculate based on chapter 5, this is what we call the indicated power out of the engine, which is the power generated inside the cylinder, which actually moves the piston in this case. Inshallah, in this chapter, we'll just try to go in details actually about some geometrical analysis of the engine and see actually how the performance of the engine will be changed when we change the geometry of the engine. That means we are changing the engine side. That means actually we are changing the engine bore, the cylinder bore, the piston bore, the diameter of the piston, and also the engine stroke, maybe the number of cylinders, the engine size itself, moving from gasoline to diesel engine in each case, how we can calculate the performance in terms of the power output and the specific fuel consumption as function of all of these parameters, so that we can compare. We can compare one engine to another engine in terms of those parameters. So inshallah, we'll start with some geometrical parameter of the engine. We'll talk about the engine terminology, and I think we have talked about this before. Engine diameter or the cylinder diameter, the piston stroke, also L, and how we can calculate the swept volume of air, calculate the mass flow rate of air, and based on that, how the engine can calculate the mass flow rate of fuel, and then how we can proceed to calculate the thermal efficiency of this engine. Inshallah, we'll be talking about all of that. We'll talk about engine power and the efficiency. We'll talk about the specific fuel consumption of the engine, the amount of fuel consumed per unit power output of the engine. Also, we'll talk about the mean effective pressure. I think we gave an idea about this. We said the mean effective pressure is not a real pressure, but it's just a comparison actually for different engines that can produce the same power for different displacement volume. For different engine size, we can get different power output. But we can use this parameter, which is the ratio between the power output divided by the displacement volume, so that we can compare, let's say, two engines with different displacement volume. We can compare their power output using what's called the mean effective pressure. Also, the engine, shabab, in case of gasoline or diesel engine, it results in emissions. So we will talk about the emission index, because there is a limit, especially for the diesel engine. Diesel engine result in a little bit higher emission in terms of CO, soot, and some particulate matter. So there should be a limit for this. We'll talk, inshallah, about the emission index, how to calculate those limits for the different engine, either gasoline or diesel engine. Inshallah, we'll talk about the engine heat balance. So as we said, the engine consumes fuel. So this is a fuel energy, M dot fuel multiplied by the heating value. But not all of this fuel will be converted to power output on the crankshaft. We should have some friction losses. We should have some cooling losses to the cooling water and the lubricating oil in this case. And also the engine itself is hot, so it can transfer heat actually by radiation and by convection to the surrounding media. So inshallah, we'll be talking about the engine heat balance. See actually this amount of fuel energy, where it goes exactly, and how it is distributed between the different output in terms of brake power, which is the final output of the engine, which is almost 1/3 of the total fuel energy. And also we'll be talking about the different losses in terms of heat losses and the friction losses. Inshallah, also we'll be talking about some engine performance characteristic. We'll see the engine map, how all of these parameters, engine power, specific fuel consumption, brake mean effective pressure, how all of these parameters can change in terms of the engine RPM or the crankshaft revolution per minute. And we'll talk about the engine map. Engine map, shabab, is the map that contains all of these parameters and relates them together, so that at any operating point, this map actually is just stored within the electronic control unit of the engine. At any operating point, the engine exactly knows the amount of fuel that should be injected in this case, and the power output, depending on actually all of these parameters and how to relate all of these parameters in order to get the best operating point in this case for minimum fuel consumption. What we need from the engine is the minimum fuel consumption and the highest power output in this case. So whenever possible, we have to get actually to approach this limit to get actually the maximum power of the engine at the minimum fuel input in this case. طيب here شباب this we'll start with some geometric analysis. As we said, this is a kind of generalized engine. The diameter of the piston itself, we call it the bore, as we said earlier. And this piston شباب inside the cylinder is moving between the top dead center and the bottom dead center, and the distance moved, we call it the stroke. So let's consider we have a general engine. This is the piston inside the cylinder, and here is the intake valve, and we have the exhaust valve, and in between we have the spark plug, or we have injector in case of diesel engine, the spark plug in case of gasoline, or injector in case of diesel. So here we have the charge. So in case of gasoline, the charge should be fuel plus air coming into the engine. The piston, this intake valve will open, and the piston will be moving down. The piston, first of all, is at the top dead center, and it will be moving down to suck the air plus fuel until it reaches the bottom dead center during the intake stroke. Type this distance شباب moved, we call it L. L, we define it as the piston stroke or the engine stroke, because usually شباب we don't have engine with different stroke lengths for the different cylinder. The cylinder in any engine are identical. So for any case, we can say actually the distance L is the stroke. This is the piston stroke, or we can call it actually as the engine stroke, because it does not differ actually from one cylinder to the other. And the diameter of the piston inside the cylinder, this diameter شباب, we call it the engine bore, or the diameter of the cylinder in this case. Once the piston approaches the bottom dead center, as you know, we have went through this, it will start the compression process, and then the spark will initiate the process to have the power. And at the end, we should have the exhaust stroke, and the exhaust gases will be leaving. And this is شباب the 4-stroke in case when we have a 4-stroke engine. Okay, we have different kind of engine. We talk about it, which is the 2-stroke. In case of 2-stroke, we don't have valve. Just we have port or opening, intake port and exhaust port, and only the piston can complete the cycle in only 2-stroke. The piston can get down and they go up. Getting down, we should have expansion plus, we should have the power stroke plus the exhaust stroke. And while the piston is moving up at the beginning of compression, we should have the intake, and then we can have the compression stroke. And this is the main difference between 4-stroke and 2-stroke. Okay. Type the displacement volume or the swept volume when the piston actually is moving between the top dead center and the bottom dead center, we call it the stroke volume. And the minimum volume here, which is we call it شباب the combustion chamber. The clearance volume, which is the minimum volume between the piston head and the cylinder head, which is the clearance volume, we define it as actually as the combustion chamber. Because usually at the end of the compression stroke, the combustion take place when the piston actually at the top dead center, or the intense combustion take place when the piston is at the top dead center. That's why we call this volume شباب the clearance volume, which is the volume defining the size of the combustion chamber, or the size or the volume at which actually the combustion take place in this case. And the total volume of the cylinder شباب, we call it the cylinder volume in this case. And we have defined very initial parameter which defines the compression ratio. We said the compression ratio is the ratio between the V cylinder divided by the clearance volume, or it is equal to V stroke plus V clearance divided by V clearance in this case. And this compression ratio, as we said, it is different from gasoline to diesel. In case of gasoline, this ranges from 8.5 up to almost 11. In case of diesel, it starts from 15 and it can go up to actually 22 in this case. Okay. What is the value of the stroke volume? This is stroke volume, which is the swept volume by the piston, swept volume of a charge by the piston for only one cycle. This stroke volume is equal to what? Is equal to the volume of the cylinder, which is pi over 4d squared multiplied by the length L, multiplied by the length L. But for an engine with a number of cylinders, we call it actually as the displacement volume, which is representing يا شباب what? Will equal to by, just I will multiply the stroke volume by multiplied by the number of the cylinder, which is Z. This displacement volume يا شباب for any car is called as what? Is named as what?
CC.
Exactly. So this is a شباب the engine, what we call the engine CC in cubic centimeter. So if this is diameter in centimeter and the stroke in centimeter, pi over 4 this square multiplied by L multiplied by Z, which is the number of cylinder inside the engine, that what we call actually the engine CC in this case. So what is the unit of this volume يا شباب? The unit is what? Meter cube per what? Yes? So this يا شباب is the displacement volume meter cube per 1 cycle. Because the piston, this is يا شباب the displacement volume of the incoming charge. When the piston moves down, it will be moving a volume of V stroke. And this V stroke will be filled by the new coming charge. This charge in case of diesel, it's only air. In case of gasoline, it is air plus fuel, but usually the ratio between air to fuel ratio is almost 15 in case of gasoline engine. So almost we can assume it actually as the incoming charge is air. So in each cycle, the piston draw actually this volume of air, which is actually the displacement volume. So this is calculated in meter cube per cycle. But in order to calculate the steady flow volumetric flow rate, meter cube per second, then in this case I have to multiply by the number of cycle per second. What is the number of cycle per second يا شباب? In case of 4-stroke engine, in case for one cycle, only one cycle, 4-stroke engine will result in how many revolution? So this piston يا شباب is connected to a crankshaft, and then this crankshaft is running actually at a given end, which we call it the engine RPM. Engine RPM is the speed of the crankshaft, which is connected to the piston in this case. All piston inside the cylinder are connected to the crankshaft to be driven at a given RPM. But in case if we have a 4-stroke engine, for one cycle, so the engine complete one cycle in 4-stroke movement of the piston. So how many revolution for one cycle in this case?
2.
For a 4-stroke?
2 revolution.
It will be 2 revolution, exactly, Shiva. So it will be 2 revolution for the case of 4-stroke, and in case of 2-stroke, it will be only 1 revolution. Because in case of 4-stroke, the piston moves down and they get up. When the piston moves down and they get up, so this is 1 revolution. Move again down and go up again, so this is a 2nd revolution. This is in case of 2-stroke for only a Shabab, this is for only 1 cycle in this case. That means the number of cycles per second, or the time for the number of cycles actually that we should have per second, should equal to the number of revolution in RPM, revolution per second, sorry, revolution RPS, revolution per second divided by 2. This is in case of 2-stroke engine, 4-stroke engine. And it should equal to N in case actually for the 2-stroke engine. So in case of 4-stroke engine, the number of cycle per second should equal to the number of revolution divided by 2. Because actually for each 1 cycle, we should have 2 revolution in this case. So the number of cycle per second for 4-stroke is equal to N divided by 2. And in case of 2-stroke, the number of cycle per second, we have 1 cycle for 1 revolution. That means the number of cycle per second should equal to the number of revolution per second. But usually, Shabab, this term N is measured in revolution per minute, RPM. So we have to divide by 60 in this case. Or we can generalize that, so we can say the number of cycle per second should equal to N divided by I multiplied by 6. Why we divided by 60? Because this N is calculated or measured actually in revolution per minute in this case. And this term, Shabab, or parameter I, is the number of crankshaft revolution per cycle. This parameter I should equal to 1 in case when we have 2-stroke engine, and it should equal to 2 in case when we have a 4-stroke engine. So the number of cycle per second for an engine will equal to the engine RPM divided by parameter I, which is the number of crankshaft revolution per cycle, which we should equal to 2 in case of 4-stroke, and it is equal to 1 in case of 2-stroke engine in this case. Okay, and based on this, Shabab, as we have calculated the number of cycles per second of the engine in terms of the engine RPM, then we can calculate the volumetric mass flow rate of air per second, not per cycle. So we have the displacement volume pi over 4d square L multiplied by z. This is meter cube per 1 cycle, the displacement volume of air for 1 cycle. So we can say the rate V dot, the volumetric rate of, or the volumetric flow rate of air to charge to the engine in meter cube per second will equal to the displacement volume multiplied by the number of cycles per second, which is N over I multiplied by 60 in this case. This is shabab, this is the volumetric flow rate. This is meter cube per cycle, and this is actually the number of cycles per second. So meter cube per cycle multiplied by cycle per second. So at the end, that should be calculated. That should calculate the volumetric flow rate of air into the engine, calculated in meter cube per second in this case. But this is about the cycle, the number of cycles per second equal to N over I by 60. So the cycle time in this case, cycle time should equal to actually the reverse of it, equal to I multiplied by 60 divided by N in this case. So this is the time, the cycle time, the time that the engine consumes in order to complete one cycle. It will equal to I multiplied by 60 divided by N, and this parameter I with the set is equal to 1 in case of 2-stroke, and it is equal to 2 in case when we have a 4-stroke engine. And this is the time that the engine consumes to complete only one cycle. One cycle, that means we have intake flow, then we have compression, then we can have a spark and have the combustion, then we can have the power stroke, and then we can have the exhaust stroke. This is actually one cycle. The time for one cycle is equal to I by 60 divided by N. That means, if we have an engine is running at higher RPM, that means the cycle time in this case will be what? Will be reduced. And this is actually a limiting case for a diesel engine. In case of diesel engine, you can look here, this is the cycle time. In case of diesel engine, as we increase the RPM, as you can see, the cycle time in this case will be reduced. But usually the diesel engine, it needs some time actually to have the different processes in terms of fuel injection, and then this fuel will mix with air, needs some time, and then it will self-ignite, and at the end we should have the combustion. And we have seen actually that this combustion should be progressive combustion, and it takes time as well. In this case, if we try to speed up the diesel engine and increase the engine speed, so the cycle time will be reduced, and in this case, most probably the combustion will be incomplete, and this will result actually in engine emission, more engine emission. And usually diesel engine, it is characterized by higher emission than gasoline engine. And that's why it is not widely spread in using compared to the gasoline engine. However, it can give higher power and it can give higher efficiency because of the emission. And even running the engine at higher RPM will result in incomplete combustion. We don't have sufficient time for combustion, and that will result in more emission like the smoke emission, CO, and some unburned hydrocarbon, and also some particulate matter. So usually gasoline engine or compression ignition engine in general, they have a smoke limit in their maximum RPM. So usually the gasoline engine, if you look at the tableau here, you will find for a diesel engine, usually the RPM is limited in case of diesel engine compared to the case of gasoline engine. Here is how we have defined the different parameters: the engine stroke, engine length, engine stroke, engine diameter, and how we can calculate the volumetric flow rate to the engine. So we have another very important parameter to the engine, which is the mean piston speed, the average speed with which actually the piston is traveling inside the cylinder. We call it the mean piston speed. But is piston speed constant as function of time? Is this speed of the piston is fixed at a given value, or it is variable while the piston is moving inside the cylinder? Is it fixed or variable? Variable. It should be variable. So you can see the piston is moving until it reaches actually the top dead center, and then actually it moves its velocity. When it reaches the top dead center, it will reverse its direction. That means the velocity should be approaching a value of 0 at the top dead center. Like this at the bottom dead center. When the piston approaches the bottom dead center, it will reverse its motion back. That means the velocity at the bottom dead center is equal to 0. So if you look at this distribution of the engine piston speed, we give it actually the symbol S, starting between the top dead center and between the bottom dead center as function of the crank angle theta. The velocity or the speed of the piston at the top dead center should equal to 0, and also the speed of the piston at the bottom dead center should equal to 0. And while the piston is moving between the top dead center and the bottom dead center, it accelerates, and it reaches actually a maximum value, almost the distance. If you are looking, this is the top dead center, and this is the bottom dead center. When the piston moves from the top dead center to the bottom dead center, we should have half revolution in this case. Half revolution, that means we have 180 degree. Okay, so this distance here, Shabab, is 180 degree crank angle revolution in this case. So usually the piston approach actually its maximum velocity or maximum speed at an angle at the middle, usually at the middle of the stroke, when the angle theta is equal to 90 degree in this case. So this is the instantaneous piston speed, which is function of the crank angle. When the piston is at the top dead center, it is 0, and when it is at the bottom dead center is 0, and in between actually the piston accelerates in this case. But usually for a given piston, usually we are interested in the value which represent actually the average piston speed. We call it SP bar or S bar or whatever you call it. We call it actually the average piston speed. But if we consider, Shabab, one engine revolution, what will be the distance moved in this case by the piston? Distance will equal to what? For one revolution, what will be the distance moved by the piston?
Which times the displacement volume.
So here, Shabab, is the piston. So piston, and this piston is connected to the crankshaft, and the crank is rotating. For one revolution, the piston is moving between the top dead center and the bottom dead center. This distance is L. Okay? So for one revolution, what will be the distance traveled by the piston?
2L.
Exactly. So the distance in this case, exactly, the distance will equal to 2L. For one revolution, the distance moved is 2L. In what time, Shabab? Time will equal to what? We said the cycle time is equal to I multiplied by 60 divided by N. And here I is the number of crankshaft revolution. Number of crankshaft revolution, we said we have only one revolution. So the time for one revolution will equal to 60 divided by N. This 60, Shabab, as we said, this is RPM. We have to divide just by 60. But in order to calculate the speed for the average piston speed, the speed will equal to distance divided by time. So it will equal to 2L divided by time, which is 60 over N. So here is 60 over N. So it will equal to 2LN divided by 60 in this case. Yeah, and in some definition, Shabab, you will find it is defined as 2LN only. In this case, N should be revolution per second. But usually this value is measured in revolution per minute in this case. So the mean piston speed, which is a critical parameter, Shabab, which is limited by the material strength, a very important design parameter. This mean piston speed, we cannot design an engine with very long stroke and we have higher RPM. So usually we have to balance it. If the engine is running with higher RPM, that means in this case we have to reduce actually the stroke distance L, at which actually the piston travel, in order to reduce the stresses within the piston. Okay, so usually piston of higher RPM should have lower stroke, and that's why in case of gasoline engine, if you look at the engine height in case of gasoline engine, because it is actually running at higher speed, so it should have lower stroke. So the height of the piston itself, the stroke distance will be reduced in order to reduce the stresses on the engine. But in case of diesel engine, usually the RPM is low. So that's why we have to increase the stroke distance. And usually, Shabab, this mean piston speed, it ranges actually between 5 up to 15. This 5 in case of compression ignition engine, and this 15, which is the highest value of mean piston speed, because in case of gasoline engine, the engine is traveling at higher speed. So this is in case of a spark ignition engine, it can approach a value of 50. But why, Shabab, in case of diesel engine, we said Engine is running at lower RPM, so the distance stroke should be high. And we said this is because we cannot run at higher RPM. Okay, so we can increase the piston stroke in this case. But why we increase the piston stroke in case of diesel engine? Why we have to increase the piston stroke in case of diesel?
For combustion, doctor.
It's related to combustion. In case of diesel engine, the compression ratio it can approach a value of 22. That will create actually very high pressure inside the cylinder. So during the expansion stroke, we need the piston to travel actually longer distance until we can actually reduce this pressure and benefit and get actually expansion for all of this high pressure. So we have high pressure value contained actually by the clearance volume at the end of the compression stroke. In this case, when the piston moves down, the pressure will be relieved and we can generate shaft power in this case. But the pressure is very high. So we need the piston to travel longer distance in this case. So we can benefit actually all of this pressure in this case. So it is something related to the efficiency of diesel engine, that it should have longer distance, bigger stroke, so that we can actually have enough time for this pressure to expand to the atmospheric pressure, then we can generate it in terms of shaft power. And that's why, Shabab, if you look at a diesel engine usually will have bigger size, and its height will be actually higher in this case compared to the gasoline engine in this case. This is, Shabab, the displacement volume, as we said, which is by stroke volume multiplied by the number of cylinder, which represents the engine CC, in this case. But look at the design here, Shabab. We need to get, this is something, for your knowledge. I will not be asking you actually to just memorize the equation, and usually I will ask a question that related to understanding. And if you ask for any formula, and the idea, Shabab, is not the exam or something, the idea is to learn. But if you have any formula in your exam and you ask it for, I will provide it for you. But just here, this is something technically related to the design of the engine. So if we have an engine here, this we call them the geometrical parameter of the engine. This is the piston. Usually the piston is connected to a crank pin to the connecting rod, and this connecting rod is connected to the crankshaft, and the crankshaft is rotating in this case. So this piston is moving from the top dead center, as we know, until actually it reaches the bottom dead center. The volume here, we said we have defined this volume as the clearance volume. But the distance here, Shabab, between the pivot here of the crank pin with the piston, with the piston pin here, actually this is the connecting rod. Connecting rod usually has a distance L. We call it L small. So L capital here, Shabab, this is the terminology. This is representing the piston stroke. But L small is the connecting rod length. And usually we have the radius. So let's just reverse this one. So let's say we are at this position. So this is the connecting rod length L. And let's say at a given position here, this is the radius of the crankshaft. We can denote it actually with the parameter A small. So this is A small. And at a steady state condition, the distance between the center of the crankshaft and the pivot here, the connection of the connecting rod with the piston, this distance, Shabab, we call it S, the small s, because we have defined the capital S as the main piston speed. The small s is the distance here between the piston pin and the center of the crankshaft. This distance S, Shabab, will be variable or constant while the engine moving, the piston moving. Should be what? It should be variable in this case. So let's say we have this engine, the crankshaft at a given angle theta, here at this situation. So how we can define the distance S as function of L and the crank radius A and the angle theta. This is the angle theta measured from the vertical. So this distance S will equal to what, Shabab? Will equal to A cosine theta, which is this part here. It will equal to A cosine theta, which is the radius, the crank radius multiplied by cosine, actually the crank angle in this case. But this distance, Shabab, here, this vertical distance here will equal to what? A sine theta. is it? So this distance for this triangle is A sine theta, and this distance is L. So this distance يا شباب will equal to what? If we set this distance square should equal to L square minus A square sine theta. So this distance S, the total distance S, will equal to A cosine theta plus this distance, which will equal to L square minus A square sine square theta. All of this actually to the power half. And these are some mathematical calculations, so you can look at it. This is L square, which is the length of the connecting rod in this case. And by this we can define the distance S as function of the crank angle theta at any time. طيب when the piston يا شباب is at the top dead center, this distance S should equal to what? When the piston is at the top dead center, S will equal to what?
A plus L.
L plus A, exactly. So in this case, at this position يا شباب, the volume of the cylinder will equal to what? When the piston is at the top dead center, will equal to V clearance. But when it move a little bit distance here is, this distance will equal to what? The difference between what? L plus A, which is the maximum distance, minus the distance S at any angle theta. And that should equal to the volume of the cylinder at any angle will equal to the clearance volume plus the volume of the cylinder, which is pi over 4 d squared multiplied by the distance. This distance, شباب, when the piston is moving down should equal to L plus A when the piston is at the top dead center minus the distance S, which is at any angle C. And by this relation, شباب, we can define the cylinder, the volume, the cylinder inside the piston, inside the volume of the cylinder inside the piston, inside the cylinder as function of the angle C. So this is function of the crank angle theta. We can just substitute it here, then we can get the cylinder volume as function of the angle, theta in this case, and function also of the clearance volume. If you divide here شباب by the clearance volume, and we define the compression ratio. Compression ratio is the V clearance plus V stroke divided by V clearance. Just divide all equation by V clearance. So it will be V cylinder divided by V clearance, which is actually the compression ratio in this case. And then we can define, then get this equation, which define actually the volume of the cylinder in terms of dimensionless V cylinder divided by V clearance, in terms of the dimensionless parameter, which is the compression ratio R, and also as function of the angle theta. So you can just go through this relation, and you can go through it this way, substitute with the distance S and divide by the clearance volume, then you can get the cylinder volume at any angle theta. Type, we set the speed of the piston شباب, the instantaneous piston speed. We have calculated the average piston speed, which is equal to 2ln divided by 60. But in order to calculate the engine speed at any time, at any crank angle theta, we need to get this value, the instantaneous value. We have the definition of S. This is the distance S, the variable distance S, which gives us indication about the movement of the piston. So in this case, if we need to define the instantaneous piston speed, it will equal to the rate of change of ds by dt. But we have the definition of S as function of theta. What is the relation between the theta, شباب, the crank angle, and the time t? The crank angle theta. How we can relate it when the crankshaft is rotating with a given angle theta? How we can relate this theta to the time t? Theta is equal to what? Theta is equal to omega multiplied by t, and omega is the angular velocity, which is 2 by n divided by 60 multiplied by time t. So theta is equal to omega multiplied by t, or we can say delta theta will equal to 2 by n divided by 60 multiplied by delta t. But we need to calculate the instantaneous piston speed, which is ds by dt, the rate of change of the distance with time, which defines the velocity. So the instantaneous piston speed S will equal to ds by dt. This is a شباب S capital, which is the piston speed. This S small is representing the distance. We said S is equal to A cosine theta plus L square minus A square sine square theta, all of this to the power half. So we have the distance S as function of theta. So I need to get the speed, the instantaneous piston speed in meter per second as function of time. So how we can calculate it, Shabab? This is S is function of theta. And we need to get it actually per time so that we can do this differentiation and we can calculate the engine speed in this case. So we can do it another way. We can say S will equal to ds by d theta multiplied by d theta by dt. We have S as function of theta here, so you can just do the differentiation and substitute here, and then multiply by d theta by dt. We have d theta is equal to 2 by n. This term is equal to 2 by n divided by 60 multiplied by dt in this case. So d theta by dt is equal to this term, and then just differentiate this equation as function of theta, then we can get the instantaneous piston speed as function of the engine, the crankshaft revolution theta. If I divide by the mean piston speed to make it dimensionless, then we can get the instantaneous piston speed divided by the average piston speed. We can get it actually as any crank angle theta. So if you have the crankshaft at any given angle theta, you can just come up to this equation and divide S divided by S average. S average or the mean piston speed is equal to 2ln divided by 60. So if you have engine RPM, then you can calculate the instantaneous piston speed at any given time in this case. Is that clear, Shabab? Is it clear?
Yes.
Yeah, this is some proofs. If you want to look at related to the engine design, how we can calculate the mean piston speed, how we can calculate the instantaneous piston speed as function of the crank angle of the crankshaft. We can just prove it through those relations. What about the air? We said the displacement volume. We have defined the displacement volume of air to the engine. V dot displacement is equal to the displacement volume, which is pi over 4d square multiplied by L multiplied by the number of cylinders. This is the volume per cycle, meter cube per cycle. And we said we have to multiply it by number of cycles per second, which is N divided by R multiplied by 60. This is actually the volumetric flow rate coming to the engine in meter cube per second. What about the mass flow rate of air? The mass flow rate of air to the engine would equal to the density of the incoming air in the intake manifold multiplied by the displacement volume, V dot displacement in this case, which should equal to the pressure in the intake manifold divided by RT. This is multiplied by the displacement volume, which is pi over 4t square L multiplied by Z multiplied by N multiplied by R multiplied by 60 in this case. And this is how we can calculate the mass flow rate of air to the engine will equal to the air density in the intake manifold multiplied by the rate of displacement volume, V dot displacement, which is the stroke volume or the displacement volume multiplied by the number of cycles per second in this case. This R, we assume this charge in case of diesel engine, this charge is air. So this R is 2.87 kilojoule per kilogram Kelvin. Or this value, if you don't remember, we can get this value from table A1 for the case of air. So the charge coming to the engine is air in case of diesel engine. And usually, in case of gasoline engines, this charge is air plus fuel. But usually, in case of gasoline engines, the air to fuel ratio is almost about 15. So the dominating gas in this case is air. So the properties are almost calculated are actually to be the properties of the air in this case. So in case of gasoline or diesel, we can assume actually that the incoming charge to the engine is only air. And we can calculate it based on the properties of the air in this case. This temperature, as you know, this is the temperature of air in the intake manifold, should be in Kelvin, and this is kilojoule, so this pressure should be calculated in kilopascal in this case. But what about in case of turbocharged or supercharged engine? This pressure in the intake manifold, in case of naturally aspirated engine, that pressure should be the atmospheric pressure. Okay. But what about in case of super or turbocharged? In this case, we use a compressor. So that means in this case the pressure at the intake manifold will be increased, and also the temperature will be increased, and that's why we said we have to use intercooler in case of supercharger or turbocharger to cool down the gases. Then we can increase the air density. Increasing the air density in case of supercharger or turbocharger will increase the mass flow rate of air, and mass flow rate of fuel will be increased, and the engine power will be increased in this case. And this is how we can calculate the mass flow rate of air. But usually this mass flow rate of air, we call it the theoretical mass flow rate of air. That should be coming into the engine. But usually the actual mass flow rate of air is less than the theoretical value due to the flow restriction. Because in case of, let's say for a gasoline engine, what kind of flow restriction do we have in the intake manifold? What kind of flow restriction? First of all, we have the throttle valve here, which is connected to the accelerator pedal. This throttle valve is just opening a limited area for the flow of air. So the air will be going around the throttle valve here, especially at part load. The throttle valve will be opened, a small opening in this case. That means the flow will be restricted with very small area. So what will happen to the velocity at the throttle valve? The flow restricted in area, so the velocity will be increased. And in this case, the pressure in the intake manifold will drop down in this case, especially at part load. At full load, this throttle valve usually is widely opening, and the area in this case is maximum, and we don't have pressure loss. But at part load condition, the throttle valve is partially open, and the area is restricted in the flow direction. So the velocity of the flow will increase. Velocity increase, that means the pressure will drop down in the intake manifold. If the pressure drop down, that means in this case the mass flow rate of air will be reduced to the engine in this case. And that's why we call this is actually the theoretical mass flow rate. The mass flow rate, which is equal to the volume of the cylinder multiplied by the incoming density of the air. But usually the piston cannot actually take all of this amount of air due to the pressure losses in the throttle valve and also in the intake manifold at the intake valve. If you look at the area around the intake valve, area is also limited, and that means we should have a kind of pressure losses in the intake valve as well. And that's why the actual mass flow rate should be less than the theoretical mass flow rate in this case. And we can define another efficiency for the engine. We call it the volumetric efficiency, which gives us indication about the efficiency of filling the cylinder with the incoming air. This volumetric efficiency is equal to the mass flow rate of air actual divided by the mass flow rate of air theoretical. Or we can say the actual mass flow rate of air to the engine will equal to eta volumetric multiplied by the mass flow rate of air theoretical. So it will equal to eta volumetric, mass flow rate of air theoretical, all of this term, which is B divided by RT multiplied by bar over 4 D squared LZ multiplied by N divided by I divided by 6. And this is how we can calculate the actual mass flow rate of air to the engine. It is equal to the volumetric efficiency due to actually the flow restriction in terms of the throttle valve and the intake valve, which reduce the pressure inside the intake manifold and reduce the amount of air flow rate to the engine in this case. So in this case, the volumetric efficiency can be defined as the ratio between the actual air flow rate divided by the theoretical air flow rate. What we need to calculate is the actual value. We need to calculate the actual performance of the engine. So any engine shabab have a definition for the volumetric efficiency as function of the engine speed. So eta volumetric, and those values are already stored within the ECU system. So depending on the engine running RPM, engine speed, so the engine knows the value of the volumetric efficiency, and the engine knows the value have indication about the actual mass flow rate to the engine. So the ECU in the engine does not calculate the theoretical flow rate. It just calculates the actual value of the flow rate. And usually, shabab, in the engine, in the intake manifold, we do have a pressure sensor. This pressure sensor uses the actual pressure of the flow rate of air, and also we have a thermometer in order to measure the actual temperature. And this is how the electronic control unit in an engine calculates the mass flow rate of air. So it measures the actual value of the pressure and temperature inside the intake manifold after the throttle valve. Then it can calculate the actual mass flow rate of air. But theoretically here, we'll just say actual mass flow rate of air will equal to the volumetric efficiency multiplied by the theoretical mass flow rate of air. طب in case of diesel engine يا شباب, this volumetric efficiency will be important, same importance like the case of gasoline engine, or we do have something else?
We don't have that.
We don't need it really, but why?
We don't
Because
have throttle valve.
Exactly, sure. So in case of diesel engine, we don't have throttle valve. Okay. In diesel engine, this intake manifold is just open, and we measure the amount of mass flow rate of air, and depending on that, the fuel injection system, the fuel pump will decide about the amount of fuel. We said in case of diesel engine, it's a quality control. It controls the amount of fuel depending on the amount of incoming air. And that's why the fuel to air ratio will be changing with the engine load. And that's why we said diesel engine is much efficient than gasoline engine, especially at part load, because it changes actually the amount of fuel depending on the amount of air. Well, the amount of air decided actually about the engine load. Okay? But in case of gasoline engine, usually the fuel to air ratio is fixed. At part load, middle load, full load, the fuel to air ratio is fixed. Okay? And this is one of the drawbacks of the gasoline engine, because it consumes more amount of fuel even at part load condition. Okay? But in case of diesel engine, we don't have this throttle valve. It is quality control. We don't have quantity control for the amount of air in order to control the load. So anyway, in diesel engine, we don't have the throttle valve, so we don't have flow restriction. So that means in case of diesel engine, usually volumetric efficiency does not have any importance in this case. But also, Shabab, in case of 4-stroke and 2-stroke. In case of 4-stroke, we have valves. So this is a kind of flow restriction. But in case of 2-stroke, just we have intake and the exhaust port. We don't have valve. We don't have flow restriction. That means also, Shabab, the volumetric efficiency almost does not apply for the case of 2-stroke engine. So usually the volumetric efficiency can be applied for gasoline engine of 4-stroke type that end the cycle, that have a complete cycle of 4-stroke movement of the piston. As I told you, the volumetric efficiency usually for a constant range of RPM, let's say from 2000 up to almost 4000 RPM of your engine, usually the volumetric efficiency is fixed in this case. But usually we have different, this volumetric efficiency, as we said, is mainly function of the design of the intake manifold. So as we have, if we have intake manifold designs that have a lot of flow restriction, that means the volumetric efficiency will drop in this case. Okay, we have two main design, Shabab, for the intake manifold. We have single plane intake manifold, and we have dual plane intake manifold. In case of dual plane intake manifold, first of all, in case of single plane intake manifold, just we have only one common intake manifold, and it distributes the air to all cylinders. This is actually the single plane. We have dual type in which we can divide actually the cylinder. We have divided to two planes above each other. Each one actually will be taking the air and distribute actually to the half of the cylinder. So let's say we have 6 cylinders. In the dual one, we will have actually a separate intake manifold to each 3 cylinders in this case. But which one, Shabab, is more better or much better than the other? Dual or single intake manifold? Which one should give me better volumetric efficiency? As you can see in this figure, Shabab, the volumetric efficiency is higher in case actually of using dual intake manifold. Dual, that means I'm using a separate intake manifold for each number of cylinders. That means we can supply more air, and also it can respond at higher RPM of the engine. And this, Shabab, can be used in the race car. In this case, when I need actually the car to speed up in a shorter time, and I need more amount of air at higher RPM, then in this case I can use what's called the dual intake manifold. Separate intake manifold to each number of cylinder, and it can provide actually more air to the engine, and also it can respond fast. It have actually higher response rate in this case. That's why it can be used with car, with the racing car when we need actually higher engine RPM. I will show you now a video just showing the differences between the single intake manifold and the dual intake manifold. But before this, Shabab, usually the volumetric efficiency, if we have a supercharged or turbocharged engine, do you expect the volumetric efficiency to be exceeding 100? The volumetric efficiency is function of flow restriction in the intake manifold. which can affect the pressure, reduce the pressure. And this pressure can reduce the mass flow rate of air. But what about if in case if we have supercharger or turbocharger? In this case, the intake pressure will be what? Will be increased. And in this case, that means the mass flow rate of air will be increased. That means the volumetric efficiency, the actual mass flow rate divided by the cylindrical flow rate, will be increased in this case. That means, يا شباب, in case of turbo or supercharger, the volumetric efficiency can be greater than 100%. Okay? So in case of turbo or supercharger, and this is one of the main advantage of super or turbocharger, that it can provide actually more amount of air to the engine. Actual flow rate will be increased in this case, and the volumetric efficiency will be increased to more than 100% in this case. So if we have efficiency, volumetric efficiency, greater than 100, that means this engine is either super or turbocharged engine in this case. And usually, شباب, for the wide open throttle, under normal condition, usually the efficiency can approach about 50, 75 up to 90%. And this efficiency, شباب, can drop down to about 25% to 30% when we have engine throttling at part load. So usually at part load condition at your car, you can imagine actually that the actual flow rate is only 1/4 of the theoretical flow rate. That means the piston here is just filled actually with quarter mass flow rate of air that should be coming in at part load. And the volumetric efficiency is about almost 25%. This is at part load condition. This volumetric efficiency can be increased up to 90% when we have actually full load condition wide open throttle. And the efficiency can be more than 100% in case when we have a super or turbocharger in this case. But we said we can improve the volumetric efficiency by using the dual intake manifold. Dual intake manifold that we are using actually separate intake manifold for each number of cylinder in this case in order to increase the volumetric flow. As you can see here, شباب, this is the volumetric efficiency for the dotted line is higher than the volumetric efficiency for the other cases, which is the dual, which is the case of single intake manifold. Single intake manifold, the equal spacing. Equal spacing, that means the same amount of flow rate will be going to each cylinder. But if we have variable spacing, so the volumetric efficiency in this case deteriorates, and this design cannot be applied because we cannot supply actually different cylinder with different amount of mass flow rate of air. That means we should have an engine unbalance in this case. But let's look at this video, شباب. It will show you the difference between the single intake manifold and the dual intake manifold.
Applications before deciding what manifold is best. Let's explore the differences between a single and dual plane intake design. A single plane design features a single plenum that receives air from the carburetor or throttle body. It distributes air and fuel to each cylinder through a series of runners. Each of the 8 runners can see all 4 barrels of the carburetor, and the runners are fairly straight and close to equal in length. These characteristics maximize airflow and optimize distribution. Dual plane designs have 2 smaller plenums that also receive air from the carburetor or throttle body. The key difference is that each plenum connects to every other runner in the firing order. So in this case, each runner only sees 2 barrels of the carburetor. This results in a higher velocity through the booster, making the engine more responsive to the driver. The inherent tuning of the 180-degree separation, combined with the longer runners, makes dual planes torque monsters in the 3,000 to 4,500 RPM range.
And this is, شباب, the main difference. It can actually result in better response to the engine, and it can provide the engine with higher mass flow rate of air in this case. By calculating the actual flow rate to the engine, then the engine ECU will decide about the amount of fuel. In case of gasoline engine, usually it is working under a stoichiometric condition, lambda is equal to 1. So the air to fuel ratio is equal to the stoichiometric fuel to air ratio in this case. Okay, so usually the engine ECU decide about the amount of fuel once it knows about the amount of mass flow rate of air. Okay, right. The mass flow rate of fuel should equal to the mass flow rate of air multiplied by the fuel to air multiplied by the fuel to air ratio in this case. So this is how we can calculate the mass flow rate of air fuel. M dot fuel equal to M dot air actual multiplied by the fuel to air ratio, the actual fuel to air ratio. And the actual fuel to air ratio, شباب, this is m dot air actual multiplied by the actual fuel to air ratio, which is fuel to air ratio theoretical or stoichiometric, multiplied by the equivalence ratio in this case. So we can define or calculate the mass flow rate of fuel, which is equal to the mass flow rate of actual mass flow rate of air multiplied by the actual fuel to air ratio. Yes. So the actual fuel to air ratio, which is the stoichiometric value multiplied by the operating equivalence ratio. And this operating equivalence ratio is equal to 1 over lambda, which is the excess air factor in this case. Okay. But if you look at the engine, شباب, here at the engine, this is actually a given engine. In the intake manifold here, the charge is coming, or the energy coming to the engine. The initial energy, which is the chemical energy. Chemical energy is equal to the mass flow rate of fuel multiplied by the heating value of this fuel, which is the lower heating value. This fuel will be burned here inside the combustion chamber, and it will be converted to thermal energy in terms of heat transfer. Heat will be released in this case inside the combustion chamber. So here we have the combustion chamber, which is almost a shape of the clearance volume, have a volume of the clearance volume. So the combustion chamber, inside the combustion chamber, we release the chemical energy and convert it in terms of thermal energy, which is the heat transfer. But usually the combustion, we don't have combustion efficiency equal to 100%, because usually we should have the mixing between air and the fuel. We should have actually some fuel that will be leaving actually unburned. We should have some unburned hydrocarbon. And also not all of the burned fuel will be burned completely. So usually we should have some intermediate product like carbon monoxide. We may have hydrogen in the exhaust gases, and all of these are kind of fuel. And still they are containing part of the chemical energy. So we cannot guarantee actually that we have full conversion of the chemical energy into a thermal energy in terms of heat. And that's why we have to define what's called the combustion efficiency for any combustion engine. The combustion efficiency is equal to the output, which is the heat added, the heat released, the thermal heat released, divided by the initial chemical energy, which is m dot fuel multiplied by the lower heating value. So the heat transfer, the heat released out of the combustion process, divided by the fuel energy, based on which we can define the combustion efficiency in this case. Because we cannot guarantee actually that this combustion is complete, and we can actually convert of this chemical energy into a thermal heat transfer in this case. So that's why we have to define the combustion efficiency. But in most of the cases, we can assume this value is equal to 1. Okay. So usually if this value is not given, we can assume the combustion efficiency in this case is equal to 1. This parameter here, let's get back to it here. The fuel to air ratio, usually, as I told you, in case of gasoline engine, it is working at lambda is almost equal to an stoichiometric coefficient. And with the engine load, while varying the engine load from part load to full load, usually the fuel to air ratio don't have much change in the fuel to air ratio. Almost we can say it is fixed. This value will be between 12 and 18. But look at in case of diesel engine, we said in case of diesel engine, it's a quality control. Depending on the amount of air coming in, we can decide about the amount of fuel through the fuel injection pump. And this amount of fuel is different from part load to full load. And that's why you'll find here, that the fuel to air ratio in case of diesel engine have wider range in this case. It can vary between 18 up to 70 in this case. 70 at part load condition, the amount of fuel to the air is very low, and it can be actually up to 18 in case actually of full load condition. In this case, we have to provide more fuel in this case. So the fuel to air ratio has a wider range in case of diesel engine because it has actually considers the quality control. It decides about the amount of fuel depending on the amount of the incoming air. But in case of gasoline engine, usually it is working under a stoichiometric coefficient, and usually the fuel to air ratio is almost constant at all loading conditions. That's why the change of the fuel to air ratio with the loading only actually it is in a tight range between 12 up to 18 value in this case. Okay. But this is how we can see the conversion of the chemical energy, m dot fuel, by heating value, through a combustion efficiency inside the combustion chamber, this energy can be released actually in terms of thermal energy. And this thermal energy will be just to create a high pressure, high temperature, and it will be converted to a mechanical energy. This mechanical energy, Shabab, we call it the indicated power in this case. So the indicated power is the mechanical power that moves the piston inside the cylinder. And this piston is connected through a crankshaft and connected through a connecting rod to the crankshaft, which should be running at a given RPM. The power that we give Shabab from the crankshaft, we call it the brake power. So the indicated power is the mechanical power that moves the piston inside the cylinder. We call it the indicated power. And we have learned how to calculate this indicated power based on the indicated diagram, on the PV diagram, based on the engine cycle analysis. The power we have calculated there, which equal to the work net, which equal to the integration of the PV of the work, the integration of the PV diagram, the area contained by the cycle. If you remember, Shabab, we have represented those cycles on the PV diagram. And we said the area contained by the cycle, we call it the network, which is equal to integration of PV. If I need to calculate the indicated power will equal to the network, which is equal to integration of PV, but this is the work, Shabab, for only one cycle. So I have to multiply by the cycle per second, which is n multiplied by I by 6. So by this we can define the intake power. So the intake power is the indicated power, which is the power that we can calculate using the indicated diagram. Indicating diagram, which is like the PV diagram. Network is equal to integration of PV, which is the work per cycle. If I multiply it by number of cycles per second, then I can calculate the indicated power, which is a mechanical power. So this is the mechanical power that moves the piston. The piston will be moving, and through the connecting rod, we can connect it actually to get a rotating motion through the crankshaft. The power that we can get from the crankshaft, we call it the brake power in this case, which is equal to the torque generated on the crankshaft multiplied by the angular velocity, which is omega in this case. So the brake power to the engine, which is the mechanical shaft power on the crankshaft, will equal to the torque multiplied by omega, and omega, which is the angular velocity, which is 2 by n divided by 60, and n is the revolution per minute of the crankshaft. Okay, so brake power, Shabab, is the final power in the crankshaft, which is the mechanical power. Indicated power is the power generated inside the cylinder that move actually the piston in order to have the reciprocating motion. So we can say, Shabab, the indicated power is the reciprocal motion power, and the brake power actually is the rotating crankshaft power in this case. And in between, Shabab, we should have what? Indicated power and the brake power. The difference should be what? This is a mechanical power, and this is a mechanical power. When we have two mechanical power and we transmit the motion, that means we should have friction losses in this case. So the friction losses is the friction losses due to the movement of the piston, and also the connection between the connecting rod and the crankshaft. This is the kind of friction losses. Also the power needed, Shabab, by the piston that is coming from the crankshaft to drive this piston during the intake and the exhaust stroke. During the intake stroke, the power should be coming from the crankshaft. It should pull down this piston. We don't have power coming from inside the cylinder. Just we have to apply power in order to move the piston during the intake and during the exhaust stroke, which we call it as what, Shabab? As the pumping work. So pumping work also is the work needed to move the piston during the intake and the exhaust stroke. It is part actually of the friction pump. And also, Shabab, in the engine. In the engine, we should have fuel pump. We should have actually a compressor. Here you can see. We can have some other devices like the compressor actually for the air conditioning system. If we have turbocharger or if we have supercharger, in this case the compressor should be driven using a part of the crankshaft power, and also the fuel pump, the air conditioning system, electrical generator, which is dynamo. All of these actually accessories are working using part of this brake power. The power required to drive all of these accessories, we can consider it also as part of the friction power, because this is a kind of losses. This is not a final output power of the engine in this case. Just to take part of this output power to drive the piston during the intake and the exhaust stroke, and also we can drive actually the engine auxiliaries in this case. So the difference between the indicated power and the brake power, indicated power will equal to the brake power at the crankshaft plus the friction power in this case. And as we have conversion between mechanical power to another mechanical power, so we have to define a mechanical efficiency. So the mechanical efficiency of the engine is the ratio between the brake power divided by the indicated power. Or we can say brake power, which is the indicated power minus friction power divided by the indicated power in this case. So the mechanical efficiency of the engine is the ratio between the brake power and the indicated power in this case. But can we measure يا شباب the indicated power? Can we measure it through experiment? Is it measurable? Which one is measurable? Brake power or indicated power? Brake power, we can measure it. But indicated power, we cannot measure it. As we said, indicated power, as you can see here, شباب, we can get it from the indicator diagram. Integration of BdV will give me the work multiplied by N over I by 60. Then I can get the indicated power in this case. But this value we cannot measure, just we can calculate from the PV diagram or the indicator diagram. But for the brake power, which is torque by omega, we can measure the torque multiplied by the omega, then we can calculate the brake power. The idea here is to measure the brake power. You know how we measure the brake power, شباب? We use a kind of dynamometer. The simplest dynamometer is the hydraulic dynamometer. Do you have an idea, شباب, about the hydraulic dynamometer? Anyone have idea? So usually we just take شباب the crankshaft, which should be rotating. Let's say it is rotating counterclockwise. We can put it actually in another drum. We call it the stator. So this is the stator, and this is the rotor, which should be the crankshaft, which is rotating. And then between here, between the two drums, one fixed and one rotating, we can just fill it with water. Okay. So once this one is rotating, what will happen to the water inside it? It will try to what? It will try to rotate. And this outer drum is free to move. It is not rotating, but it is free to move. So what will happen to the outer drum? It will try also to what? To rotate. In this case, we can just connect it with a wire, and then we can just put some loads here. And then this wire will apply a force in this direction through a distance, let's say distance B, and then we can apply loads. That means we have a force here, which is equal to mass multiplied by G. This force will be resisting applying a torque in the reverse direction. So the flow that is rotating inside will try to rotate the outer drum in this direction, counterclockwise. But this load will actually try to apply torque in the reverse direction. And at a steady state, this force can just, or the torque applied by this force, which is the force multiplied by the distance B, should equal to actually the output torque of the crankshaft in this case. At a steady state, when this point is not moving, either this side or this side, that means this torque, external torque, is just balancing actually the torque coming by the crankshaft in this case. And then we can calculate this torque. Once we have this torque, we have the engine RPM, then we can calculate the brake power in this case. This is how we can run it by experimentally using what's called the dynamometer, the engine dynamometer. Okay. Dynamometer, this is a kind of hydraulic dynamometer. There are different kinds. We can have electric dynamometer, in which we can have this rotor, the crankshaft, we can just insert it in a magnetic field, and then we can just remove one piece or two, and then there is another way to have difference in the magnetic field. Then we can calculate also the brake power of the shaft in this case. And usually the electric one is the most common one, because this one is a kind of mechanical one, but it's still used. It is used in the experiment. I think we have one here in the heat engine lab. You can look at it if you want. Okay, so this is the brake power, which we can measure, and the difference between brake power and the indicated power, which is the mechanical efficiency of the engine. The difference is the ratio between the brake power divided by the indicated power. The mechanical efficiency, شباب, this mechanical efficiency is function of the engine design and the function also of the engine speed. Almost its value is about 90% at the normal operating RPM, which is about 2000 RPM, and it can be reduced to a value of 75% at the maximum engine speed. But usually, شباب, this value, due to the throttling, in case of throttling, using of throttling valve, it results actually in lowering the pressure in the intake manifold. Lowering the pressure in the intake manifold, that means in this case, the pumping work will be increased. Okay, pumping work will be increased. That means the friction losses has been increased. So that means the mechanical efficiency will drop down in this case. So under part load condition, the mechanical efficiency will be reduced because the pressure in the intake manifold will be reduced due to the small opening of the throttle valve. Pressure in the intake manifold reduced. That means the intake stroke will be done at lower pressure. So that means in this case, شباب, the pumping work, which is the work during the exhaust and the intake stroke, will be significantly comparable to the indicated work, which is the net work out of the cycle. So that means in this case, the pumping losses are high, which is part of the friction losses. That means the mechanical efficiency will drop down. And usually, شباب, at the idling condition of the engine, when the engine is running, but the car is not moving, like when you are just sitting in a signal or something. So just the engine is running, but we don't have any output power in this case. That means the mechanical efficiency will equal to 0 in this case, because the brake power is equal to 0, and all of the generated indicated power inside the piston is just consumed in the friction power. And in this case, the mechanical efficiency will be a 0 value under the idling condition in this case. So here, شباب, this is an indication diagram. Usually the torque, شباب, is not function of the RPM. Look here, the brake power is equal to torque multiplied by omega. So brake power is function of the RPM. And as the RPM increase, as you can see here, the brake power will be increased in this case, but up to a certain limit. When the RPM approach a value of 6,500 RPM, when you reach actually the rated power of the engine, or the rated brake, the maximum rated power of the engine, in this case, if you raise the engine RPM more than this, the brake power will be reduced in this case, because the friction loss power increased too much, and in this case, the overall efficiency of the engine will be reduced. So the brake power is function of the engine RPM. It increased when the engine RPM increased up to a certain limit, which is the rated power, at which when we increase the engine speed a little bit more, in this case, it will result in lowering the brake power, because most of the engine power in this case will be increased actually or consumed in order to control the friction losses in this case. So it will be consumed actually in the friction losses. The friction will become significant in this case, and the brake power will drop down. But the torque, شباب, here is not function of the RPM. Usually the engine torque is fixed with the RPM, but usually at lower engine speed due to the heat losses, usually the torque is a little bit reduced, and at higher, much higher engine speed here, above the rated speed, you'll find the torque also will be reduced. This is actually because the timing for the intake valve has been much reduced. In this case, the amount of mass flow rate of charge to the engine will be reduced. And that's why the engine RPM will be reduced. But usually the engine RPM, the torque, is not function of the RPM, but the brake power is function of the RPM, okay? And as we said, when we increase the engine RPM, in this case, the brake power will be increased. But you can see here, شباب, at your car, if you reach this limit, 6,500 RPM, and you approach it, the rated power, then in this case, if you increase the RPM more than that, the rated power will be reduced in this case, because most of the power will be consumed to overcome the friction in this case. The terminology, شباب, maximum rated power, this is actually the rated power or the maximum power that the engine can reach. But we should not actually run the engine at this power actually for longer time. This power the engine can produce, but actually for a very short period of time. The engine cannot be actually running actually at this power for longer time. But we have normal rated power. Normal rated power, this is the engine power, the maximum engine power that the engine can produce, but actually the car or your engine can be driven actually at this car for longer time, as you want. So we have maximum rated power, the maximum power that the engine can produce, but we should not run the engine at this power actually for longer time. We have normal rated power, which is the maximum power that can be produced by the engine, but we can run the engine actually at this power for longer time. And we have the rated speed, which is the maximum engine speed at the rated power in this case. This indicator diagram here, Shabab, we have learned in chapter 5. Area A plus C, this is representing the indicated work, the gross indicated work by the piston during expansion and the compression stroke. Area C plus B, which represents the pumping work during the intake and the exhaust stroke. And the net indicated work is the difference between both of them. The indicated net work minus the pumping work. We call it actually the net work. So it will be the net work will equal to area A minus area B in this case. And we see the Shabab, I think I said all of that. In case of supercharger or turbocharger, the pumping work is a gained work or a positive value, because compressor apply actually more pressure for the air in the intake manifold. And the intake stroke take place at pressure higher than the atmospheric pressure. And that's why we have a power during the intake stroke due to the high pressure of the incoming air. In this case, we have power to drive the piston. We don't need power to come from the crankshaft. And that's why, Shabab, the net work for a turbocharged or supercharged engine will equal to the area A, which is the net work during expansion and exhaust stroke, plus area B, because the pumping work in this case is a gained work by the compressor. So it is a positive work in this case. Okay? Is that clear, Shabab?